Every second, billions of invisible particles pass straight through your body. They move through walls, the ground, even the entire planet, without leaving a trace. These particles are called neutrinos, or more dramatically, ghost particles. They are among the most mysterious phenomena in modern physics. Unseen, almost impossible to detect, and yet full of secrets about the universe. Scientists believe that by studying ghost particles, we might unlock some of the greatest cosmic mysteries, exploding stars, black holes, and perhaps even the nature of the universe itself. Stay with us until the very end, because we'll reveal the massive experiment buried deep in Antarctic ice that is already catching ghost particles, and why its discoveries could change everything we know about the cosmos. The first question is, what are ghost particles? They are everywhere. They pass through everything, and yet we never notice them. Neutrinos, often called ghost particles, are some of the strangest and most elusive particles in the universe. They earned their ghostly nickname because they barely interact with anything. Billions of them shoot through your body every second, and yet you feel nothing. They travel through walls, oceans, and even the entire Earth as if matter simply doesn't exist. Physicists classify neutrinos as elementary particles, fundamental building blocks of matter. But unlike protons, neutrons, or electrons, neutrinos seem almost disconnected from their surroundings. For decades, scientists believed they had no mass at all. Only in recent years did experiments prove that neutrinos do have mass. So small it's almost unimaginable, but still enough to shake up the standard model of physics. Why do they matter? Because neutrinos are born in some of the most extreme environments in the universe. Inside the nuclear furnace of the sun, in the violent collapse of massive stars, in the chaotic jets of black holes, and in cosmic ray collisions across deep space. They are silent messengers, carrying unique information about events that no other form of radiation can deliver. Unlike light, X-rays, or charged particles, neutrinos don't get blocked, absorbed, or bent on their journey. They fly straight and unaltered, making them the perfect messengers of the cosmos. If we can decode them, we gain a direct window into places and events that are otherwise forever hidden. But that is the problem. Detecting them is nearly impossible. Almost all neutrinos pass through any detector without leaving a mark. Only with enormous, highly sensitive instruments, buried deep underground or frozen into Antarctic ice, can scientists occasionally catch one. The hunt for neutrinos is therefore as frustrating as it is exciting. They are invisible, untouchable, and yet they may carry the keys to understanding the deepest mysteries of the universe. The next question is, where do they come from? To understand neutrinos, we must explore their origins. Where they come from reveals why they are so important. Our nearest and most constant source is the Sun. Inside its core, nuclear fusion reactions generate unimaginable numbers of neutrinos. They are so abundant that billions of them stream through every square centimeter of your body each second. Without neutrinos, our knowledge of the Sun's inner workings would be far more limited. But the Sun is just the beginning. Neutrinos also pour out of the most violent explosions in the cosmos, supernovae. When a massive star collapses and explodes, almost all of its energy, around 99%, escapes as neutrinos. These ghostly particles are therefore not just byproducts, but the dominant signal of such cataclysms. Even more extreme sources include black holes and neutron star collisions. When matter spirals into a black hole or when two neutron stars merge, exotic processes unleash torrents of neutrinos. Unlike light, which may be trapped or scattered, neutrinos escape freely, giving us rare insights into these mysterious objects. Neutrinos also emerge from cosmic rays, ultra-energetic particles racing through space. When these rays smash into atoms in Earth's atmosphere or elsewhere, they generate showers of secondary particles, including neutrinos with mind-boggling energies, far beyond anything we can produce in human-made accelerators. For scientists, neutrinos are therefore like cosmic messengers. They carry clues from places we can never visit and events we cannot otherwise observe. A single detected neutrino can point back to a distant supernova, the turbulent environment of a black hole, or even unknown processes still hidden from physics. Each ghost particle caught is like a postcard from the farthest, most violent corners of the universe, written in a language we are only just beginning to translate. Ghost particles live up to their name because they are nearly impossible to catch. Detecting neutrinos is one of the hardest challenges in modern science. The reason lies in their weak interaction with matter. Unlike electrons or photons, which constantly collide and interact with atoms, neutrinos pass almost untouched. Statistically, a neutrino could travel through light years of solid lead without ever hitting anything. This means that nearly all neutrinos streaming through your body pass unnoticed. Out of the billions per second, only the rarest fraction interacts with an atom. To detect even a handful, scientists build massive, highly specialized observatories. In Japan, the Super-Kamiokande detector is a giant underground tank filled with 50,000 tons of ultra-pure water. It is buried beneath a mountain to shield it from background noise. Inside, hundreds of light sensors wait for the faint blue flash that appears when, against all odds, a neutrino collides with a water molecule. At the South Pole, the IceCube Neutrino Observatory uses the Antarctic ice itself as a detector. More than 5,000 optical sensors are embedded deep under 2 kilometers of ice. When a neutrino interacts, it produces a flash of blue Cherenkov light that those sensors can record. Even with such enormous instruments, detections are rare, sometimes just a few events among billions of passing neutrinos. Yet each detection is a triumph. It provides data about the neutrino's energy, its origin, and the astrophysical event that created it. Catching ghost particles is like finding a single needle in a mountain of hay, but the reward is worth it. Every captured neutrino is a direct messenger from the invisible universe. Neutrinos are more than strange particles. They could hold the answers to some of the deepest mysteries in science. Take supernovae. When a star explodes, almost all the energy leaves as neutrinos. By measuring them, scientists can peer into the very heart of stellar death throes, insights no other signal can provide. Each neutrino from a supernova is a direct line to processes that are otherwise hidden from us. Then there are black holes and active galactic nuclei. These extreme regions launch powerful jets of energy, but we don't fully understand how. Neutrinos escaping from these environments may carry clues about the mechanics of matter falling into black holes. Neutrinos may also be tied to the mystery of dark matter. This invisible substance makes up most of the universe's mass, but has never been observed directly. Some theories suggest that neutrinos or related particles could reveal how dark matter works, or even be part of it. Even the nature of neutrinos themselves is a mystery. Do they act as their own antiparticles? Why do they have mass, and how did they acquire it? Answers to these questions could force scientists to rewrite the standard model of physics and open doors to entirely new theories. In short, neutrinos are not just cosmic oddities, they are keys that might unlock the secrets of exploding stars, the engines of black holes, the origins of dark matter, and even the foundations of the universe itself. That is why scientists worldwide are racing to capture them. Every neutrino detected is another piece of a puzzle that could transform physics forever. Despite major progress, the quest to understand ghost particles has only just begun. Scientists are now building even larger, more sensitive detectors to push the field forward. In the United States, the DUNE project, Deep Underground Neutrino Experiment, is underway. It will fire an intense neutrino beam from Illinois across 800 miles of rock to a massive detector in South Dakota. This could reveal whether neutrinos are their own antiparticles, a discovery that would revolutionize physics. Meanwhile, the IceCube Observatory in Antarctica is being upgraded. Already, it has detected neutrinos from faraway galaxies, possibly linked to supermassive black holes. Soon, with increased sensitivity, it will probe even deeper into cosmic mysteries. Japan is building the Hyper-Kamiokande detector, set to dwarf its predecessor. With millions of tons of water and thousands of sensors, it aims to catch neutrinos from supernovae in distant galaxies, offering unprecedented detail on stellar deaths. The future of neutrino science is a race against the invisible. As our detectors improve, so will our ability to read the universe's most secret signals. Ghost particles may soon tell us about phenomena that light and gravity cannot. The central question is no longer if we will understand neutrinos, but when, and how that understanding will reshape everything we know about the cosmos. Neutrinos are not just elusive, they are essential, and the discoveries ahead may change physics in ways we cannot yet imagine. Tell us in the comments, do you think neutrinos will one day unlock the secrets of the cosmos? And don't forget to subscribe for more deep dives into the future of science and space.